A few weeks ago, I was on vacation in Northern California when a wildfire started burning nearby. The fire itself never threatened where I was staying, but the smoke did. For about 24 hours, the air quality became so bad that I changed my plans and stayed indoors. It was a reminder that you don't have to be anywhere near the flames for a wildfire to affect your life. And this summer, that experience is being repeated across large parts of North America. Today, we're going to look at how the changing climate has led to a greater fire danger, why determining what caused wildfires is more complicated than it sounds, and how smoke from distant fires can eventually find its way to you. Welcome to the podcast. I'm Dr. Mack, and this is the Climate Translation. When we talk about wildfires, we tend to focus on the moment they begin. What started the fire? Was it lightning, a campfire, a down power line, maybe a piece of equipment? Those are important questions, especially when investigators are trying to determine responsibility. But from a meteorological standpoint, I'm more interested in a different question. Once that first flame appears, what happens next? To understand, let's go back to something many of us may have learned in science class, the fire triangle. Every fire needs three basic ingredients: heat, fuel, and oxygen. If you take away any one of them, the fire can't continue. That's why when you pour water on a campfire to remove the heat, it goes out. It's why a fire extinguisher can smother a flame by separating it from oxygen. But a wildfire operates on a much larger scale. Oxygen is not the problem. There's plenty of that in the atmosphere. And once something provides enough heat for ignition, that part of the triangle is satisfied as well. So that leaves the fuel. And in a forest, grassland, or shrubland, fuel is everywhere. There are trees, grass, pine needles, fallen branches, leaves, and dead shrubs. Even the layer of organic material sitting on top of the soil can be a fuel source. But not all fuel burns the same way. If you've ever tried to start a campfire with damp wood, you probably know this already. You can hold a match underneath it, you can add paper, you can even blow on the flame. But much of the energy from that fire first has to evaporate the water inside the wood. Now, compare that to a pile of dry twigs and leaves. One spark can be just enough. The difference isn't the amount of fuel, it's the amount of moisture that's inside it. The fuel source can respond especially quickly to changes in atmosphere. Dead grasses, leaves, and small twigs have a lot of surface area compared to their size. They can gain or lose moisture relatively quickly as the atmosphere humidity changes. A large log responds more slowly, and a living tree is different as well. Its moisture depends not only on today's weather, but what's been happening over weeks, months, even years. Has there been enough rain? Is the soil dry? Has the vegetation been stressed by drought? How much water is the plant losing through its leaves? So when meteorologists and fire managers look at wildfire danger, they're not just looking at today's temperature. They're looking at the climate, the condition of the entire landscape. And then you add in wind. Wind can transform a manageable fire into something very different. This is what I saw in Northern California. Wind supplies fresh oxygen to the flames. But more importantly, it bends those flames towards unburned vegetation. That preheats the fuel ahead of the fire. Wind can also carry burning embers away from the main fire, and those embers can land hundreds of feet, sometimes even farther, away from the flames and start new fires. Firefighters call that spotting. Now, instead of fighting one continuous fire line, crews have many fires starting ahead of them. And the terrain matters too. Fire generally moves uphill fast. As flames burn vegetation on a slope below, heat rises and warms the fuel above the fire before the flames actually reach it. The steeper the slope, the more efficiently that can happen. So fire behavior becomes an interaction between three things: the fuel, the weather, and the terrain. Change any one of those, and the same ignition can produce a very different outcome. And as our climate has warmed, it has changed the background conditions in which that ignition occurs. A longer period without rain dries vegetation. An intense heat wave increases moisture loss. A warm spring can melt mountain snow earlier and give landscapes more time to dry before the hottest part of the summer arrives. And when those conditions occur together, the landscape becomes much more receptive to fire. Think about two identical matches dropped into two different places. One lands in damp grass after several days of rain. The other lands on vegetation that has spent weeks drying under the hot, sunny weather with low humidity. The ignition is identical, but the outcome is going to be completely different. And that's why saying a wildfire caused by lightning, a power line, or a person doesn't really tell us everything we need to know about why that fire became so large or so difficult to control. The spark tells us how the fire started, but the condition of the landscape tells us what happens afterwards. And there's a way meteorologists can measure one more important part of that condition. It tells us something about how strongly the atmosphere is demanding moisture from plants and fuels at any given time. It's called vapor pressure deficit. And as our atmosphere warms through climate change, that number is becoming increasingly important to understanding wildfire risk. So what is vapor pressure deficit? The name sounds complicated, but the idea, it really isn't. Think about a warm summer afternoon. There's an amount of water in the air, but there's also an amount that's needed for that air to be at saturation. The vapor pressure deficit, or the VPD, is the difference between the two. The larger the difference, the greater the atmosphere's demand for moisture. You can think of it as an atmospheric thirst. When VPD is low or small, the atmosphere is very moist and it's not demanding any additional moisture, or very little. When VPD is high, or a large number, water can evaporate more quickly from soils and dead vegetation, and plants lose water more quickly through their leaves. And temperature plays an important role in this. As air gets warmer, the amount of moisture or water vapor it can hold increases, and thus the amount of water vapor or moisture needed to reach saturation increases. That means if the temperature rises, but the amount of moisture in the atmosphere doesn't increase, VPD goes up, and the atmosphere becomes thirstier. That's why relative humidity doesn't always tell us everything we need to know about how quickly a landscape can dry. Imagine two afternoons with the same amount of moisture in the air. One is relatively cool, the other is extremely hot. Even though the amount of moisture is the same, the hotter atmosphere has a greater or larger vapor pressure deficit. It has a greater need to suck in water to fill up that gap. It creates a strong demand for water from the landscape below. And plants respond to that demand. During photosynthesis, plants have tiny openings on their leaves called stomata. These openings allow carbon dioxide to enter. But there is a trade-off. When they're open, water can escape. On a day with a high vapor pressure deficit, a very thirsty atmosphere, plants can lose water quickly. Some respond by closing those openings to conserve moisture, and it's a useful defense, but it also limits the carbon dioxide they can pull in, thus slowing photosynthesis and putting plants under stress. If the conditions continue for days or weeks, vegetation can become increasingly dry, and dead vegetation responds even faster, Grass, leaves, pine needles, and small branches, they exchange moisture directly with the surrounding air. Under hot, dry conditions, they can become more flammable in a very short period of time. Now put that all together with what I discussed earlier. A spark occurs, but if the spark lands where the VPD is high and fuels have been drying for an extended period, the fire is entering a landscape that is much more prepared to burn. This is one reason researchers have become very interested in the vapor pressure deficit. Across the western United States, studies have found a strong relationship between VPD and the amount of land burned by wildfire. And as temperatures have risen due to climate change, the atmosphere's ability to create those high VPD conditions has increased as well. It doesn't mean that every hot day is going to produce a wildfire. A wet winter or spring can provide important moisture, but it can encourage vegetation growth that may become fuel later in the season. Wind, terrain, vegetation type, the ignition still matters. But VPD gives us another way to understand why two landscapes can look similar but behave very differently when fire arrives. And perhaps more importantly, it explains something about climate change that can be easy to miss. A region doesn't necessarily have to receive dramatically less rainfall for wildfire conditions to become more favorable. Sometimes the atmosphere simply is better at sucking that moisture away. So when a major wildfire occurs, one of the questions we ask is, what caused it? And as you can tell, the question is more complicated than it sounds. Let's say investigators determine a fire started when lightning struck a tree. Well, you know what caused the ignition, but have you explained why it burned 100,000 acres? Not really. To understand that, you have to ask several questions. In addition to what started the fire, you have to ask what allowed it to spread. What conditions were present in the landscape when the fire began? What was the VPD? These are not necessarily going to have the same answer. In the United States, people cause the majority of wildfires. Campfires, equipment, vehicles, power lines, debris burning, fireworks, even arson. They all can provide the initial spark. Lightning is a major source, particularly across remote parts of the West and the vast boreal forest of Canada. But once that ignition occurs, the atmosphere really doesn't care where the spark came from. A fire started by lightning or one started by a person is going to respond to the same wind, the same humidity, and the same fuels. And then we have the condition of the forest itself, and this is where forest management enters the conversation. For much of the 20th century, the goal in North America forests was to suppress fire as quickly as possible. The goal was to protect communities and valuable timber. But fire is a natural part of the forest ecosystem. Small fires remove grasses and shrubs, fallen branches, and other vegetation. When you suppress the fires, the fuel can accumulate. In some forests, that can give a future fire material to burn and potentially make it more difficult to control. That's why prescribed burning and forest thinning can be useful tools. But here's where the conversation goes off track. Forest management and climate change are often presented as competing explanations. Was the fire caused by poor management? Was it caused by climate change? Scientifically, those are the wrong questions, because they can influence fire risk at the same time. A forest can contain high amounts of fuel because of its management history, and that same forest can experience weeks of extreme heat, high vapor pressure deficits, and very little rainfall. Add in some strong winds, provide an ignition, and you've got the factors to contribute to a major event. And the importance isn't the same everywhere. A dense forest in California is different from a grassland in Washington. A remote boreal forest in northern Canada is different from either of them. Different ecosystems have different fire histories, different fuels, and different relationships with people. That's why scientists are careful when attributing changes to wildfire activity to any single cause. Climate change does not explain every fire. Forest management does not explain every fire. And neither does lightning or human carelessness. Instead, we have to look at how each factor changes the probability of a particular outcome. Science isn't always trying to identify one culprit. Sometimes it's trying to understand how several conditions come together at the same time. So when you hear investigators have determined what caused a wildfire, remember that they've only answered one part of the question. They've told you what lit the match. But understanding why the landscape burned the way it did requires looking at a lot of other variables that were already waiting when the match was struck. So far we've talked about what happens around a wildfire, but fire doesn't just change the landscape where it burns, it also changes the atmosphere. When vegetation burns, it releases a complicated mixture of gases and tiny particulates in the air. I know in the fire that I experienced, one thing they talked about was PM 2.5. It's an important element in human health. The name refers to particulate matter smaller than about 2.5 micrometers. That's very small. We're talking about something that is 20 to 30 times smaller than a human hair. Because these particles are so tiny, they can remain suspended in the atmosphere and travel with the wind. And they're small enough to penetrate deep into your lungs when you breathe them. That's why you can be hundreds of miles away from a wildfire, see no flames at all, and still receive an air quality alert on your phone. But where that smoke goes depends on the atmosphere. The heat from a wildfire causes air above it to rise, and that carries smoke with it. How high that plume rises depends on the intensity of the fire and the structure of the atmosphere above it. If the atmosphere is stable, smoke usually remains trapped close to the surface. That can cause terrible air quality near the fire. But if the atmosphere allows the smoke to rise higher, the winds above the surface can carry it farther away. And those winds don't all blow in the same direction or at the same speed. A smoke plume a few thousand feet above the ground may travel very differently in the air than we've experienced at the surface. That's how smoke crosses state lines, national borders, even entire continents. And we've seen remarkable examples of that with the Canadian wildfires. Smoke produced in remote forest can travel south into the United States, affecting air quality across the Midwest, the Northeast, and sometimes even farther away. Under extreme conditions, a wildfire can even create its own thunderstorm. They're called pyrocumulonimbus clouds. The intense heat creates a powerful updraft that can carry smoke high into the atmosphere, occasionally even reaching the lower stratosphere. But smoke doesn't need to travel that high to become someone else's problem. Ordinary winds in the lower atmosphere are more than capable of carrying wildfire smoke hundreds or thousands of miles. So that brings me back to where we started today. A couple of weeks ago in Northern California, I wasn't threatened by the wildfire itself. I didn't have to evacuate. I wasn't watching flames approach where I was staying. But I still lost a day of my vacation because the atmosphere carried the fire to me, not as flames, but as PM 2.5 smoke. And millions of people across North America are increasingly familiar with that experience. That's an important change in how we should think about wildfire risk. The people living beside a burning forest face dangers those of us hundreds of miles away may never experience, but the effects don't stop at the fire line. Once smoke enters the atmosphere, the weather can take over. Winds determine where it travels, and stability helps to determine whether it stays near the ground or goes higher. Eventually, changing weather conditions determine when cleaner air finally returns. A wildfire can begin as an event on a landscape, but once the smoke rises, it becomes a meteorological event as well. A wildfire may begin as a single spark, but climate helps to determine the conditions waiting when that spark arrives. As our atmosphere continues to warm, understanding how heat, moisture, and weather influence those conditions are becoming increasingly important. Because climate change doesn't have to light the fire to change the way it burns. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.